Hello, I'm Verdi Arbusto, and this is the Schumann Resonance Harmonics channel on YouTube and on Facebook. Thank you all for being here. I appreciate you coming out and giving me your love, your comment, your support. For those who've given me funding on PayPal, thank you very much. You have helped me create the studio so that it sounds really, really good. Okay, so remember to like, share, comment, and subscribe to your favorite content creators so you can see more of their videos as they create content for you and me. Okay, so it is it's like 11 o'clock. It's on the 25th of Wednesday. This is ending of Monday. Today was a nice day overall. Okay, so what we're going to do, this is part 4. I just want to get into it. This is part 4 of the video on a new ELF receiver. I want to make sure I get the name correct. A new portable ELF Schumann resonance receiver. Design and detailed analysis of the antenna and analog front end. Okay, so I've already been through 3 of these already. I've given a better introduction to the material than that. And there is links in the description for you to see yourself. Like I said, I've already gone through 3 videos of this. We've talked about, there was the abstract, the introduction, and the last part that we talked about was the magnetic induction coil, which are these right there. Okay, so this part here, I'm going to be talking about, this is a little bit of a longer section to this. And that's one of the reasons why I wanted to do this in sections so that, you know, each one wasn't too long. The last one was like 40 minutes, and that was definitely not as long as this one. All right, so I'm just going to get into the material. Let me get all set up. Okay, onward and upward. All right, so this part, we're going to be talking about the signal acquisition chain, which is essentially this picture here, which is like right below it, which shows you the stages. That's essentially the picture that I had in the thumbnail at the beginning of this that shows you the individual stages that the signal has to go through to become processed in order for you to recognize them as Schumann resonances on the spectrogram graphic. Okay, so I'm going to read, like I said, I'm just going to read. And a lot of these videos, I think you should know, they're more intended for you to just kind of put them in the background. They don't have much visuals to them. So this is kind of more of an audio book for you to read. Okay, so that's one of the reasons why I just want to get into this and get it. So there's not much extraneous stuff. So you can kind of watch this over and over or listen to it over and over as need be. All right. Okay, so I think that's what we're reading. Let me get into it. Analog front end, regardless of its architecture, carries out filtering and amplification of received signals to the level required for the data acquisition module. Okay. And like I said before, I have over here on the right-hand side, I have the same basic thing twice. This is the actual material from the website, or you can also download this as a PDF, by the way. I'm happen to go here to the website because I just have it up on my browser. But I also have this as a PDF format. Okay. So I want to have the original there to the left, and the one on the right here that I have in red. This is what's going to be posted in the Word link, the WordPress link for you to go to. Part of this is in the description of the video. The rest of this, the bulk of this, is probably a couple WordPress links, so that's not over one overwhelming thing. So that's sort of what I'm doing here. So you can, this is the massive text, and the one on the right-hand side, you can follow along a little better, maybe. I don't know. Maybe or maybe not. I don't know. But that's the intended purpose of that. And like I said, this is really just for audio so that you can kind of put this under the background. There's not much visuals to this. There's only like 5 or 7, 8. I think there's 8 or 9 figures. There's a couple tables which aren't really that visually exciting. So this is pretty much an audio book for you to listen to. Okay. All right, so I read that part. Specifically in this work, the filtering and amplification setup consists of 6 cascading circuits which provide amplification and filtering of the induced very low amplitude voltage signal, few tens of nanovolts, coming out of the coil. Figure 3 shows a block diagram of the electronic chain. Okay. Our filtering and amplification chain consists of the following stages: preamplifier, low-pass filter, and notch filter, double notch filter, double low-pass filter, high-pass filter, and a variable gain amplifier. Since the maximum current of the signal condition setup does not exceed 100 milliamps, one 47-hour ampere hour, battery with a 2.5 watt solar battery charger extends autonomy for more than 45 days. Data acquisition and processing system has already been presented by Tatsis et al., and that's reference 29, for the purpose of digitizing signals of the entire ELF band with 16-bit resolution and an adjustable sampling rate. Okay. And we're seeing figure 3. Let's get the full-size image here. Okay. And this is, again, the signal conditioning setup. And it says, filtering and amplification chain. The architecture of our Schumann resonance detection and measuring system is shown in the schematic diagram. 2 amplifying stages, amplifier, and 4 active filtering stages are the signal conditioning setup that provides signal strength enhancement and bandwidth limitation in order to achieve Schumann resonance detection and measuring. The output of the last amplifying and filtering stage is connected to data acquisition system, which is DAQ. That system exploits digital signal techniques and methods, providing signal, spectrum estimation, and measuring. Okay, did you get all that? That's a lot. For better noise performance and less signal degradation and distortion, the preamplifier was mounted directly on the coil inside the plexiglass container as shown in figure 2. Okay, so that is figure 2 up here. You can see it's right there. They put it right on the coil. Alrighty. Preamplifier. Yeah, now we're getting somewhere. The first stage of the signal conditioning setup, which is the preamplifier, is shown in figure 4. The preamplifier stage is based on a non-inverted operational amplifier technology. The RC circuits at both VCC and voltage CC and voltage EE were used for decoupling purposes at both positive and negative supply voltages. Similar RC decoupling circuits were used in every stage of our filtering and amplification chain. The amplifier's gain was equal to 35.5, and the 3 decibel cutoff frequency due to the RC filter in the output is 0.24 hertz. In order to achieve additional low noise performance, the OPA 209 operational IC, that's integrated circuit, amplifier was chosen because it exhibits very good low noise performance. For further investigation, we designed and implemented 2 more preamplifier stages that are based on inverted operational amplifier architecture and instrumentation amplifier technology, respectively. Taking into account our antenna coil architecture, we provided both simulated and measured results. Okay, so I see what they did. These results indicated that both of these two alternative preamplifier stages had limited performance. All right, let's say this again. All right, I want to make sure we all get this here. It says the results indicated that both of these two alternative preamplifier stages had limited performance. That means that they were limited in what they could do and what they could, the ability of them to amplify a signal to a point where it's able to be recognized by the data acquisition. Okay, so it needs to have a certain minimum level of line level signal coming in that you could recognize it as a signal and not a noise. I think that, hopefully that explains it. Okay. Boop, boop. And this right here is the preamplifier. All right, so I'm showing you the different, this is the schematic of the preamplifier, okay? And I'm not going to go into what all the signals are. You know, you don't necessarily need to know this. It's not what's important. Just you see that there is a schematic diagram here. All right, preamplifier. The first stage of our amplifying and filtering stage is based on non-inverted operational amplifier technology. Non-inverted operational amplifier technology. The main goal is to provide low noise amplification on the extra low level induced voltage at the induction coil terminals. Resistors R7 and R3, R7 and R3 through feedback connection define the gain voltage as well as the output RC filter stage. R2, C3 eliminates flicker noise for better performance. We also used bypass capacitors at both positive and negative power supplies. The voltage gain amplifier is the last stage of our amplifying and filtering chain. That stage is also based on non-inverted operational amplifier topology, having a potentiometer in feedback instead of a fixed resistor value component. That potentiometer offers an efficient way to adjust total gain. And basically a potentiometer is a variable resistor. It allows you to select a certain level rather than it being fixed by rather than it being fixed by a fixed resistor. Okay, so the resistor has a certain value, certain ohm rating that it's going to stay at. Okay, the variable potentiometer moves that. So it's not a fixed frequency, it's something that you can adjust based on the conditions that are in the atmosphere. Okay? All right. In order to evaluate the total RMS, that means root mean squared, and I'm not going to go into that right now because that's an equation, okay, of the RMS, root mean squared, equivalent input noise voltage of our preamplifier stage, we designed and implemented an equivalent input noise measurement platform. The test measurement platform consists of the following cascaded stages. Okay. 1, the flat response amplifier with a gain voltage of 392. Okay. The second order band pass filter with band pass voltage gain of 2.4 upper cutoff frequency of 52 hertz and a lower cutoff frequency of 1.3 hertz. All right, so this, you got to see this here, all right? It's important to notice this, that the Schumann resonance antennas, all of them, have a built-in cutoff, right? And due to the filtering, the amplifier, all of the electronics, there is a inherent cutoff frequency range beyond which they cannot measure. All right, it's really important. This particular one here is measuring up to 42 hertz, and that is the upper limit. 46 is the upper limit of the Schumann resonances. So for any antenna maker, any antenna that's registering, that is detecting Schumann resonances, only needs to go up to 52 hertz. And you see the lower cutoff there is 1.3. So it's not 0. It's not even 0.3. It's 1.3. Okay? So these are, again, this is just what's important about this is the built-in limitations of the machine itself. These machines aren't picking up gamma. They're not picking up X-ray. They're not even picking up terrestrial radio. They're not picking up things in the kilohertz. They're not picking up things in the megahertz. They're not picking up X-ray. They're not picking up gamma. They're not picking up optical light. They're not seismic meters. The range of detection for the majority. This is a common. This is a common statistic for the Schumann resonances. They only go up to, or the Schumann resonance detecting machines. There's a narrow range that they can detect, and they only go up to 52 in the case of this, or 40 in the case of Tomsk, or as we saw earlier, 3 to 29 hertz for one of the Chinese stations. I think it was Chinese or Japanese stations. Okay. The Mexican station, they're only operating up to 50 hertz. Okay? So this is really important to understand. The first most important thing to understand, here's a person who's doing the antennas. He's telling you this is what the operational limits of the receptivity of the antenna is. We ain't going any further than 52 hertz in measuring this. So if there's a blast that's happening due to an earthquake or some solar craziness, that's not of the Schumann resonances, and that's not going to be measured. All right, the variable gain of flat response amplifier with voltage gain range from 1 to 21. Okay? The maximum total gain of the three-stage amplification chain is G subchain equals 19.75 hertz. I'm not sure if it's 19,000 or I would imagine it's 19,757. Okay. I'm just looking at how they're using the periods and the punctuation on this. So I think that's 19,757. Okay. Feeding this chain with the amplifiers, PAs, preamplifiers output, we obtain a total gain of G sub PA times G sub chain equals 701,374, where G sub PA is 35.5. In order to measure the preamp equivalent input noise, the preamplifier output is shorted to ground, and the output is connected to the three-stage amplification chain. All these circuitries are installed inside a metal box for electromagnetic protection and are battery powered. Figure 5A. Figure 5B shows the noise obtained at the output of the above amplification chain, where peak-to-peak value is, give or take, 95 millivolts. Or micro. I think that might be... No, milli. Sorry about that. 95 millivolts, considering that the amount of noise represents 99.904% of the additive white Gaussian noise, AWGN, corresponding to the area between the probability density function, PDF, and the plus or minus 3.3, I'm not sure what that signal is, what that symbol, not signal, what that symbol is. Okay. All right. All right, let me cut myself. Okay. So we have, this is figure 5, so we have the metal box, which is our shielding, and you see the pack of batteries that they have here. The monitoring is all battery packed, and that's something to remember, that these antennas are powered. The amplifier needs power, everything needs a power. So when you see, just as a public service announcement, just to do yourself a favor, when you see that there is a data blackout stripe, the first thing you should assume is that the power went out. That's it. The first thing you should assume is that the power went out. Just the power went out, okay? There could be other things going on. There could be other things happening. Maybe the cable was cut or something, I don't know. But the first guess of the data voids is that the power went out. Right? Just the first assumption should not be that it is a timeline shift. Is that the best you can do of coming up why there's a data void? If your cell phone wasn't working because the batteries went dead, would you assume it's a cell phone, that your cell phone was experiencing a timeline shift? Maybe you would. Maybe you are that kind of a person that assumes that things that aren't working, electronics that aren't working, is a timeline shift. I don't know. This is all belief anyway. Okay. So, you see that's the battery backup. This is our neat little kit that we have for the electronics, the box for the amplifier. All right. And this is a test, I would say. All right. So A, the metallic box for electromagnetic protection and battery powered. B, experimental preamplifier voltage input noise, which is 20 microvolts per division. All right, so each one of these is 20 microvolts. Each division here is 20 microvolts. All right. For electromagnetic shielding, we used a metallic box that accommodates the under-test preamplifier stage and the necessary amplifying and filtering stage for noise investigation. Also, we use batteries for power supply of the total circuitry. The SMA output provides noise measurements using digital oscilloscope. In order to achieve efficient estimation on equivalent input noise, the preamplifier inputs are shorted and the power supply is provided. Measuring the total output noise at several sequential snapshots, we made observations that confirmed datasheet noise parameter values. Okay? Okay, all right, we're here. Taking into account that the total bandpass gain is 701,374, we deduce that the total RMS equivalent input voltage noise is 20.5 nanovolts, or negative 154 decibel volts. Okay, so when we are seeing those spikes, hold on a sec, let me readjust myself. Okay, I think that's good. So, right here. All right. The equivalent input voltage noise is 20.5 nanovolts, or 154 decibel volts. Okay. So, I'm pointing this out because this is showing you, right there, that's showing you, there, it's showing you, that is what those peaks are on the chart, on the graphs. When you see those amplitude spikes, that is how to read it, right there. 154 decibel volts. And it's a negative. It's actually a negative decibel volts, okay? Because these are so weak, it's in the negative scale. You got to remember that. So when we see the amplitude spikes, it is decibel volts. And in fact, it's actually decibel electron volts, technically. All right, but what do I know? Okay. This leads to an equivalent input noise. This leads to an equivalent input noise of 2.8 nanovolts over the square root of a hertz for the bandwidth under consideration. This measured equivalent input noise of our amplifier is in accordance with the equivalent input noise given by the manufacturer of OPA 209. That is 3.3 nanovolts over the square root of a hertz at 10 hertz and 2.25 nanovolts over the square root of a hertz at 100 hertz. At 100 hertz. Okay. This measured noise value is the worst case noise appearing in the input, since our band pass filter is not a brick wall but second order Sallen-Key, and in addition it includes any extra noise due to the PCB environment, etc. In addition to the equivalent input voltage noise, the PA exhibits also an input current noise that adds extra noise when flowing through the induction coil resonance. The total RMS input current noise at bandwidth 1.3 to 2.5.2 hertz given by manufacturer is 4.21 picoamps, I think. All right. A key element for efficient noise reduction of the entire SR measurement setup is to choose a preamplifier with equivalent input noise as low as possible. This noise will be added orthogonally to the thermal noise of the coil, and that's N sub C. In our case, for R subcoil equals 3,160 ohms, we obtain. Okay, so here's the first equation. I don't know how to read that. Since the two noises, N sub A and N sub C, are orthogonal, we obtain total noise for the SR measurement setup. And orthogonally, if I'm not mistaken, orthogonally means at kind of an acute angle, or there's a certain, it's at an angle, acute angle. I'm not sure more than that, but that's, if I understand correctly, orthogonally means that. Okay. Oop. All right, and then we have the next equation here, and they're showing you. All right, so they're just showing you what they're doing here with the equations. I'm not sure what they really mean, so don't ask me. I'm not a math person. Which means that the preamplifier adds another 0.65 decibel noise to the resistive noise of the coil. When the PA, the preamp, is connected to the induction coil, the noise due to the input current noise will only be 13.9 nanovolts. In the above-mentioned noise measurement setup, the current noise contribution is 0, since the input is shorted to ground. Okay, I see why they did that. Okay, so we're at the filtering state. Our amplification and filtering chain has second to fourth stages that are based on Sallen-Key and twin T-notch filter architectures. The Sallen-Key filter topology is a populated architecture mainly due to the fact that the filter performance exhibits very limited dependence on the operational amplifier performance. Also, the ratio of the largest passive component value to the smallest passive component value is very low. This is an important benefit in implementation. The twin T-notch filter architecture offers versatile and efficient methods to develop and implement band stop filters using commercial operational amplifiers and standard values of passive components, which are resistors and capacitors. Moreover, using a resistor potentiometer at feedback line may provide adjustments that affect both the bandwidth and the resonance depth. In particular, the second stage of the amplifying and filtering chain consists of a second-order Sallen-Key low-pass filter and a 50 Hz twin T-notch filter in cascading connection, figure 6. The band pass gain of this stage is adjusted to 35, and the negative 3 decibel cutoff frequency is 46 Hz. The signal attenuation at 50 Hz is 10 decibel. All right. So when you, just for understanding, when they talk about attenuation, they talk about, it's kind of let me actually get the definition for this, because I have a certain definition of what I believe it is, but I want to get the right definition for this. Okay, according to Webster's Online, they basically say the reduction of force, effect, or value of something, okay, and it also means the reduction of the amplitude of a signal, electric current, or other oscillation. All right, so that's what I thought it was. All right, so you see what they're doing is decibels is the intensity of the signal. Okay, so when they're attenuating a signal, they're stopping it at a certain intensity level. So when the lower part of the Schumann resonance, it's like a resistance to it. It provides, there's a filter, there's a various electronics which filter out parts of the signal. It makes it, they'll put up a resistor in the line and makes it so that the signal has to work harder to go through that circuit. So instead of having to work harder to get through the filter, it just goes around it. All right, so that's part of one of the things that we're looking at, that when we talk about the Schumann resonance signal, there's part of it that it's valid, it's good, and that's the part that we're looking at, because there's not a filter there. Okay, but then at a certain point where you don't want it to go past 50, right? So they want it to stop at 46 hertz, which is where, this is what they're telling you. They want it to stop at from 3.5 to 46 hertz. This is the area of the signal that they're looking to get. So the attenuation is relatively small, so that it easily goes through that section, that processing part of it. The signal goes through it easily because it's not attenuated. Okay. Now they're saying the signal attenuation at 50 hertz is 10 decibels. So the attenuation at the 50 hertz is actually more than 3. It's like 300 times, because the first one is negative. This is a negative 3 decibels, which is not much. Negative 3 decibels is not much. But then you have, after 50 hertz, you have 10 decibels. So negative 3 times 3 would be 1. And then you have 10, so that's 30. That's roughly, it's more, I don't know. I don't think the math is actually quite like that. I think it's more than just 3. I think it's like more than 300%. But you get what I'm saying. I'm not good at math, but I just want you to have a kind of understanding that this number here, the negative 3 decibel cutoff, okay, is a less lesser intense number than this 10 decibel cutoff at 50 hertz. So what they're saying is they're providing a resistance over 50 hertz, so that it's not picking up more than 50 hertz. It's having the signal has much more difficulty going over the 50 hertz attenuation mark than it does actually recording the signal itself. Hopefully that makes sense to you. Made sense to me in my head as I said it. All right. So this is the we're talking about again the filtering stage. Let me scoot in here on this. All right. The low pass and notch filter. Okay, let me. Whoop. The schematic shows a second order silent key low pass filter and a twin T 50 hertz notch filter. These circuits are active filters providing amplification and signal bandwidth limitation, mainly in the frequency range of 50 hertz. Both the two architectures exhibit several advantages and remarkable performance in ELF range. The passive components needed to implement these circuits are commercially standard values and exhibit low noise performance. Signal bandwidth and total gain requirements are taken into account. Okay. Okay, the third stage of the chain consists of two cascaded 50 hertz twin T-notch filters. The band pass gain of this stage is 3.3, and the negative 3 decibel cutoff frequency is 46 hertz. The attenuation obtained at 50 hertz is 35 decibels. Okay, and that's different from the one that we just read. Okay, the fourth stage of our amplifying and filtering change is based on the fourth order silent key low pass filter topology. It has two second order low pass filters in cascading connection. The band pass gain of this stage is 10 at the frequency range 1 to 45 hertz, and the 3 decibel cutoff frequency is 46 hertz. The fifth stage of our amplifying and filtering chain involves a silent key high pass filter technology. The band pass gain of this stage is 5, while the 3 decibel cutoff is 1.8 hertz. Okay. All right. Now we're on to the variable gain amplifier. The last stage, sixth, of our amplifying and filtering chain is a variable gain amplifier. It is based on the non-inverting topology, similar to preamplifier topology. Both input and output have passive single pole RC high pass filter with cutoff frequency 0.016 hertz. These filters reduce the flicker noise efficiently. The measured frequency response of this amplifier stage exhibits quite a flat response at the frequency range of interest, which is 1 to 46 hertz. The amplification of this stage ranges from 1 to 20, or adjustable through a potentiometer, which is again a variable resistor. Thus, the variable gain amplifier also offers a versatile way to adjust the total bandpass again. That feature plays a key role on installing the portable Schumann resonance system at various environments due to adaptability. Okay. Alrighty. That should be 20. Okay, I'm going to do some editing here with you all present. Okay. Total gain and response. Okay. For more efficient electromagnetic shielding of all amplification and filtering stages, each stage is individually iron shielded as shown in Figure 7. Moreover, all stages are mounted on a cup of a ferromagnetic box, thus assuring additional shielding of the chain. See Figure 8, where the cup closes the metallic box. Okay, I'm not sure what that all means, but you see that you have seen the picture and the illustration of it. Table 3 summarizes the bandpass gain of each stage as well as the achieved total gain. These results are achieved through studies and investigation on all 6 stages in terms of performance and efficiency, both using simulation and experimental measurements. The total simulated and measured frequency response of our amplifying and filtering chain is shown in Figure 9. In case the bandpass gain of the variable gain amplifier has a prefixed value of 1. Okay, I'm going to read that again. The total simulated and measured frequency response of our amplifying and filtering chain is shown in Figure 9 in case the bandpass gain of the variable gain amplifier has a prefixed value of 1. Okay? I'm just reading what they're showing. Ready? Okay, how are we doing here? Want to make sure to get the whole picture in there. You can see that. Nice, nice. Okay. Iron shielding of each stage, e.g., which is exemplia gratis, the double notch stage. All right, so they're showing you the filtering, the double notch stage. The amplification and filtering chain stages are each arranged inside a metallic box for electromagnetic shielding. In order to achieve efficient noise performance, we designed and implemented such metallic boxes. These implementations provide electromagnetic shielding protection from any interference. Taking into account the extra low-level induced voltage signal at antenna terminals, we should eliminate any source of interference that will provide signal degradation and distortion. Okay, so you see how much time and effort they're putting into filtering the signal so that you're only getting what you want to get. And you, look at this, you see this right here, it says double notch right on it. So there are filters that you can get. You can buy filters apparently already made by certain companies, and that is something to look into if you're planning on making a Schumann resonance receiver yourself. Okay, electromagnetic shielding metallic box. Electromagnetic shielding metallic box. Okay? Apart from the preamplifier stage, the amplification and filtering stages, 2nd to 6th, are all arranged inside a metallic box for electromagnetic shielding purposes. The total PCB circuits are mechanically adapted to the inner side of the top box. That arrangement allows us to adjust the total voltage gain through applying torque to the potentiometer screw in the variable gain output. Variable gain amplifier, I'm sorry. A connector at the other side of the metallic box provides power supply at the amplification and filtering stages through an outer switch. And I'm looking here for the switch, and I don't know where that, I'm sorry, not the switch, the turning screw. I'm not sure where that is. Okay. Okay. And this is table 2. You can just see what they're you know, these are the values here that they're given. The preamplifier is 35. All right. Low pass and notch filter, 3.5. Band pass gain value. So the band pass filter is filtered at that frequency for this 35. This is 35.5 decibels of attenuation. Okay, and this is 3.5 decibels. It's 3.3. All right, so that's more or less how to read this. Okay. And this right here, figure 9. Okay, we got a nice. Whoop. All right, so this is a chart. Oh, I think it almost all fits in there. Nice. All right. So this is a chart here, figure 9. Simulated an experimental frequency response of filtering and amplifying system. In order to make efficient investigation on the total amplification and filtering chain, we provide simulated and measured results. These frequency response results that help us to make useful output signal level and bandwidth considerations. Both simulated and measured results provide a flat frequency response at the frequency range of interest. Also, these results indicated that the 50 Hz power line signal component exhibits extra low level that eliminates any output signal degradation and distortion, mainly due to induction coil saturation effects. All right, so you see what they're doing here is they've kind of mathematically figured out what their frequency response is. Okay, and this is the 50 Hertz. You see this here. This is the notch. It's filtered this frequency, so whatever is coming at 50 Hertz frequency gets filtered out, gets notched out. So the notch filter, you see this notch right here. So that's what that means. When they call it a notch filter, it means it's just taking out that frequency range of 50 Hertz, so that anything that appears in that frequency range, say for example the commercial electric power supply grid that operates at 50 Hertz, so they have notched this out so that it's not reading that, it's not artificially reading that 50 Hertz signal and giving you a false reading that there's something that's there when there isn't anything there. Okay? All right, I'm just going to kind of I'm just readjusting this here. Okay? I'm almost done with the video, but I'm readjusting it now. Okay? Alrighty. Okay, so I read all that. All right. From these curves, it is obvious that there are little declinations between the simulated and experimental results. Declination. These declinations are mostly observed at upper and lower cutoff frequencies, that's 1 and 43 Hertz, as well as 50 Hertz. Okay, so you can see that's what they're telling you. There's a kind of a dip at 1, and then it kind of, or not a dip, but a kind of a declination is going off of what your axis is. Declination, it's an angle. So when it says declination, this is a declination there, and this is kind of a declination there. Decline, it's declining. All right. The passive components, which are resistors, capacitors, we used, exhibit limited parasitic resistances and reactances that may provide degradations on the total circuitry response. Also, the printed circuit board microstrip lines may have a possible impact on the total response results. Oh, this is interesting. Also, I'm reading this again. Also, the printed circuit board microstrip lines may have a possible impact on the total response results. Okay, that's interesting. So once again, I'm telling, oh, hello. Oh, I was already open. All right. So once again, I'm telling you that, or I'm showing you from the reading that the electronics themselves, the machines themselves, the detectors themselves, the antennas themselves have a certain resonant frequency. They provide a certain resistance that is telling you, parasitic resistance. That's what that's telling you. That the resistors and the passive components have an inherent electronic function that needs to be considered in it. So we're talking about a latency, we're talking about, the pre-printed circuit boards on the microstrip. On the pre-printed circuit board microstrip lines, okay, have an effect on the total response. So this is something to remember, that when you're looking at the Schumann resonances and the spectros and you're trying to understand what's going on, it could be a byproduct. In certain cases, it could be a byproduct of the machine itself whirring away that you're hearing. Okay? In order to measure... Okay. Oh, hold on. There we go. Okay, I'm back. I had to adjust things. I'm not sure where I was and things, so I'm going to go back to where I thought I was and kind of pick up from there. So if I am repeating myself, I apologize. I just had to do a bunch of stuff, and I'm getting back into this. So thank you all for bearing with me. I appreciate that. Okay, so I just talked about the impact on the total response of the printed circuit board microline. All right. In order to measure the signal chain response at the frequency range of 1 to 100 hertz, we used our automated measurement setup that exhibits limitations on measuring and recording extra low amplitude signals. These limitations mainly provide the declinations between simulated and measured frequency response results at 50 hertz frequency. Okay. For further investigation on the noise of the total system, we provided simulated results on equivalent input RMS noise at each input of our amplifying and filtering chain stage, which is table 4. At these simulation results, we assumed that the upper and lower limits of the noise bandwidth are 1 and 40 hertz respectively. Okay, and so give you the figures there, and I'm going to just leave it for a minute so you can see this. I'm going to drink a cup of coffee. Nice, nice. Okay, I'm going to go back to the text now. Okay. All right. From these results... Okay, hold on a sec. Okay, from these results, it is convenient that the total output noise of the implemented amplifying and filtering chain is mostly defined by the induction coil thermal noise and less by the preamplifier noise. All right, I'm going to read that again. From these results, it is convenient that the total output noise of the implemented amplifying and filtering chain is mostly defined by the induction coil thermal noise and less by the preamplifier noise. Well, that's interesting. Okay, I'm not sure what all that means, but that's interesting. The induction coil thermal noise, that is interesting. In particular, experimental measurements on several outdoor environments indicate that voltage gain amplifier stage should have a band pass gain of 4 for better performance on Schumann measuring and recording resonances. In that case, the equivalent RMS input noise of the latest amplifying and filtering stage approximates to 5135.3 nanovolts. Besides, each system stage has its own impact on the total output noise. That impact is determined by each stage noise value and its sequential arrangement at our amplifying and filtering chain system. The last consideration is based on the fact that the stage voltage noise experiences lower gain and thus exhibits less effect on the total system noise as it arranges closer to the output of our chain. We also provide simulated results on noise figure, NF, in decibels at 10 hertz for each stage of our amplifying and filtering chain. Okay. And so I'm not going to read this. I'm just going to leave it up for a minute so you can see this yourself. Okay. All right. Okay, so we're at measurements in the field. Okay. Measurements on the field, results. All righty. In order to confirm and improve the system's operation, we made short-term measurements, few hours, mainly in almost, quote-unquote, almost white zones in the region of Epirus, which is northwest Greece. Epirus? Those spots, as well as geographical coordinates and distance from the EM pollution, are shown on Table 6. Except the last spot, which is the chapel at Doliana, all the other places are in the countryside, not suitable for long-term housing of our Schumann resonance detection and monitoring system. Finally, the measurement equipment have been installed at the 5th spot, a chapel located at a small gorge, 570 meters above the sea level and around 1 kilometer away from man-made electromagnetic pollution. Okay? Figure 10, the Schumann resonance system starts measuring on 19th January 2016 with concurrent recordings with few time gaps due to electronic equipment maintenance and local interference. Okay? Since June 2016, ETA Labs Schumann Resonance Measuring Station has been added to the list of worldwide Schumann Resonance Stations, 30. Oh, we got to look that up. Okay. And so they're telling you here, once again, with a few time gaps due to electronic equipment maintenance and local interference. So once again, they are referring to data gaps. Time gaps, data gaps, that's what they're talking about. When you see on the stream, on the spectrogram stream, where you see a data void, that would be indicative of a power outage or down for maintenance. First two things, just to assume, if you have to, if you're going to assume something, it should be local to the machines itself, which would be either maintenance or local interference. Okay, so when they get a signal relative to local interference, when they get a signal, a lot of times, not always, but a lot of times when a signal is received that's out of bounds, okay, like I showed you, they have the certain limitations, the certain boundaries that they're looking for the signal. When a signal is outside of that, when information is outside of the signal range, then it will often just kind of what's the word I'm looking for? It truncates the data, or it just indicates that data may be problematic. That the data which is off the chart or off the scale is indicative of either local interference or something wrong with the system. So a lot of times the AI, the algorithm of the machine itself, will cut out because it's believing that there's local interference. Okay, I think that's the best way to describe that. All right, so here, this is the, actually I don't think I looked at this yet. All right, oh nice, all right. So this is a list, I'm not going to go through this. So this is a list of the locations that they tried, the first 5 locations they tried before this, where they were getting, they were measuring, and for some reason it wasn't good to put it because it's out in the country, but they used it as a measurement. They tested this system in a number of different places, and some are, the one distance from EM pollution. So you're seeing they're all at least 1 kilometer away from EM electromagnetic EM pollution. Okay, actually, I'm going to stop it right here. I have in my own personal notes, part 5 is where we were going to start measurement on the field. Okay, so this I've given you a little update, little teaser of where I'm going to go to next, in case you needed it, in case you wanted it. Because I just looked at everything and it's like I'm already in an hour. The video is already in an hour, and this is going to be going into a lot more stuff that I'm not going to get into right now at this point. All right. So at this point, the video is done. I've gotten to where I need to here. I'm going to pick up the next one right at the beginning of this, so you got a little preview of what's coming next on the measurements in the field. All right. So on that cheery note, thank you all for being here. I appreciate everyone coming. I appreciate the comments. Like, share, comment, and subscribe. And if you want to see more from your regular content providers, go over to their channel. Thumbs up some videos. Look at old videos. Comment on it. Go over there. Do your part, please. Right? Everyone, oh, I didn't see your thing. Well, when was the last time you came to my channel? Right? When was the last time you went browsing through my channel? There's a lot of stuff for you to go through. So if you don't see your regular content providers for a while, go to their channel and comment on some videos. And I guarantee you'll see their videos up. All right. So that's just a hopefully friendly public service announcement to YouTube community. And thank you for all your care, your love, your comments, your sharing, your feedback. Thank you, everyone. I really appreciate it, because if you weren't here to kind of provide your cheery attitude, this would not be worth it, and I wouldn't be here doing this. Okay, so on that cheery note, thank you all for being here, and I hope to see you soon. And I'm going to be starting part 5 like right now. All right, so thank you all for being here. Have a great and wonderful day. Namaste.